So again, my goal in this part of the course, after proposing to you the idea of divide and conquer, is to give you as many examples as I can, given the time limits of divide and conquer, and you will see many more examples in the tutorials. So, to recap, how to design a divide and conquer algorithm. We said that there are a number of steps you have to follow. The first step is you have to divide the overall problem, or the data given associated with the problem, into as many divisions as it makes sense. The divisions has to be done in a way so that the output of the division process is a problem that you started with, but it's just of a smaller size. The second step, as we've said last time, is you are going to actually solve the smallest meaningful problem or subproblem that you can identify. And the size of the problem here is very important, because it has to be small enough so that your conquering or your actual solution to the problem is almost trivial to encode. And since this is not the final solution, what you are doing in step number 2 is to come up with solutions to smaller problems. You have to combine all those solutions into a meaningful solution that is actually the solution you're looking for the initial problem that you started with. Now, after this recap, let's move on to this example. Here are the details. Suppose you're given a sorted array of zeros and ones, so only 0 and 1. By the way, this is a nice problem because it doesn't have to be really 0 and 1, but talking about it in terms of zeros and ones are nice because it just simplifies the explanation. But you could replace the zeros and ones with any two other values that are sortable. So it could be like the color red and green, for example, or genes. So let's do it on zeros and ones. Let's say you have an array of zeros and ones, and they are sorted. So the zeros comes first, and then the ones. And you would like to know the first one that appears, the first value 1 that appears. So as you see here in the examples, if you get this array 0, 0, 0, 0, 0, 0, and then a 1, the index of the first one is index number 6. And if you get an array without ones, then the index of 1 is going to be -1, which means it does not exist. Now, what is required is to think of a divide and conquer algorithm that solves this problem. Obviously, there is a brute force approach. You write a for loop, you start scanning from the beginning, and when you find the first one, you just stop, you break the loop. But that one is going to be O of n, because in the worst case, you're going to go from the beginning of the loop all the way till the end of the loop, or the beginning of the array all the way till the end of the array. So I want to teach you something here. Before you jump into thinking about solutions, whether it's divide and conquer, greedy, or dynamic programming, look at the problem statement and try to come up with some observations. Observations are remarks or insights from the problem statement that will help you to develop a solution. You know by now, what is divide and conquer? You're going to divide. So the input array, ultimately you have to divide it somehow. But how you actually proceed in developing a divide and conquer has to do with the quality of your observations. And this is something you can only get by solving lots of problems. So I'm showing you here two observations that, hopefully you will be able to develop parallel ones for similar problems. So let me read it. It says, the first observation, for any two subarrays that are a result of a split, the leftmost bit in each subarray is a candidate answer. So if we keep track of where is the earliest one, that could help. What is that saying? I'm going to split the array. I know, because this is how divide and conquer works. So I say I'm going to pick the value in the middle, the bit in the middle. Now, I have the left subarray and the right subarray. What should I do? And what should I do is related to what are my observations. I'm looking for the first one. So let's say the array in the left are zeros. Well, to check that, I have to go and check the whole array. But if I check, which is not good, right? Because this is not divide and conquer anymore. But if I just check the first bit to the left, okay, and the first and the last bit, and I find that both of them are zeros, then everything in the middle is also zeros, right? So picking a value in the middle and checking the first bit and the last bit will tell me something, whether I should look further into this half of the array, or I should just drop it. Because if I'm looking for a 1 and the first bit is 0 and the last bit is 0, then everything in between is the 0, because the data is sorted, then I'm just going to ignore all of that. Now, if I find the first one is 1 and the last one is 1, which is more important? It's actually the left one, because I'm looking for the left one, the first one to the left, because that would be the first one in the array. Okay? So these two observations, let me read the second one. It says, for any subarray that is the result of a division, and since the array is sorted, checking first bit and last bit and finding that they are zeros, then we can ignore all of that subarray. Okay, so this is the one I started by explaining, since it's impossible to have a 1 in the middle. Now, if you look at the first one, what is it going after? Let me read it again. It says, for any two subarrays that are the result of a split, the leftmost bit in each subarray is a candidate answer. So what am I thinking here? Well, if I split and I have two subarrays, the leftmost bit in each one of the two subarrays has significance to me, because the leftmost bit, if let's say I have a left and right subarray, the leftmost bit in the right subarray being a 1 is interesting. The leftmost bit in the left subarray being a 1 is interesting. Of the two, I should keep the one in the left subarray. Okay? Maybe this point is not that clear. It will be clear hopefully in the following slides. But this is an observation that has to do with the ordering of the values. Since I'm looking for the first one to the left, then the leftmost bit of any subarray is more interesting than anything that comes after it. Because if there is any result I'm looking for, and since I'm looking for a 1, if the 1 exists in the leftmost bit, then I have found the candidate answer. Not necessarily the answer, but it's a candidate answer. Okay? Now, by now, I think you should be thinking, oh, this looks like binary search. And you're right, actually. The idea of binary search appears many times when doing divide and conquer. And this is an example, actually, of applying a variation of binary search to solve this problem. So again, the idea is simple. The divide is divide the array to two parts using the midpoint. So I'm just going to get the length of the array and divide that by 2 integer division. I will get the index somewhere in the middle. And now I have a left array and a right array. Okay? Now, what I'm going to do, and this is why I'm saying this is similar to binary search, I will look at both subarrays left and right of the midpoint. If either of them starts with a 0 and ends with a 0, I'm just going to ignore it. That's why it's similar to binary search, because we do the same idea or the same approach in binary search. Okay, and this is what the conquer is saying. If a subarray is all zeros, ignore. Now, what if it's not all zeros? All zeros means the first bit is a 0, the last bit is a 0. But what if you get the right subarray, say it starts with a 0 and it ends with a 1? Okay? Now, if the left subarray starts with a 0 and ends with a 0, the right subarray starts with a 0 ends with a 1, then what you're going to do is you're going to work with the right subarray, because it starts with a 0 and ends with a 1, so there is a 1 somewhere. Okay? So I will continue working with the right subarray. I will completely ignore the left subarray. And this is again the idea of binary search. Now, but now we start deviating from binary search. The approach of ignoring half or ignoring a part and working with the other part is binary search like. But we stop there in terms of comparison with binary search. What we do next is slightly different. What we're going to do is, with the part that we're not going to ignore, we're going to keep track of where is the one, where is the leftmost one we have found. Because if I have a stream of that starts with zeros and then ones, and then I split it, I might still get zeros and 1. So I need to keep track or find the leftmost one. Okay? And since I am splitting and the array, the subarray further into two further smaller subarrays, I want to make sure that I pick the leftmost one. Okay? Because if I have a sequence of zeros and then ones, and then when I split, I get also a sequence of zeros and then ones, and then only ones on the right side. The leftmost one in the right side is not the first one. The first one exists in the left of what I'm working with. So I have to split that further. Okay? So let's look at the code. Hopefully it's going to be, clearer, more clear when we look at the code. And notice it looks somewhat like binary search. So the array is passed, and I have a low and a high references or indices. And as long as the low didn't cross the high, so low is equal to, less than or equal to high, I find the midpoint. This is the third statement that says int mid equal to low plus high divided by 2 integer division. And then I do the following. I say if array of mid equal to 1 and the mid equal to 0, or array of mid minus 1 equal to 0, I want you to think with me what's going on here. If I say array of mid is going to be somewhere equal to 1, and the mid itself is equal to 0. If array of mid equal to 1 and mid equal to 0, that means I am working with array of 0. So if array of 0 equal to 1, there is no way there could be anything before that, because this is location 0 in the array. So I'm just going to return mid. Now my other statement that my other condition that I'm checking for here, if array of mid equal to 1 and array of mid minus 1 equal to 0. So this is the first one, because we're got zeros and then suddenly 1, and that will be the case. So if either of these two cases, array of mid equal to 1 and mid equal to 0, or array of mid equal to 1 and array of mid minus 1 equal to 0, which means it's the first one after a 0, I will return mid. I have found it. This is the first one that appears in the array. Now if it's not, let's see what I'm doing. I'm saying else. If array of mid equal to 1, I have found that this is a 1. So mid is somewhere. It's not in location 0. Okay? Mid is somewhere. It's somewhere. Let's say array of 5 is equal to 1. Well, I cannot conclude that this is the first one. But if I have found a 1, and since the first condition failed, which is in the previous if statement, array of mid minus 1 is not equal to 0. Because the first condition was checking if array of mid equal to 1 and array of mid minus 1 equal to 0. So if I go to the line that says, after first one lies to the left of mid, my condition here is if array of mid equal to 1, then there has to be another 1 before it. Because what's before it is not a 0, because we checked in the above if statement. I hope that is clear. So I'm going to move the mid to make it mid minus 1. So I'm going to move the high. The high is going to make it mid minus 1. That's why it says high equal to mid minus 1. Okay? Now, what that means, after array of mid, this statement says if array of mid equal to 1, and if it succeeds, this means everything after it is a 1. But I don't care, because I'm not interested in those. I'm interested in the first one to the left. That's why I move the high before the mid. Now, if this statement, if array of mid equal to 1, fails, this means array of mid is equal to 0. This means everything before it are also zeros. So I will come here, which is low equal to mid plus 1, meaning that my 1 is to the right, because I'm still looking at zeros. The 1 is still to come. Okay? And that will be basically everything I need to check for, and then I go up again to the while statement to find another midpoint and do the same check again. Okay? That we just explained. Now, in Geeks for Geeks, you can get this piece of code. You don't have to type it, and you can see a simulation of it running and understand how it works. Now, I'm showing you this for two reasons. First of all, it doesn't have to be recursive, because I know some of you will be, reluctant from using recursion. Well, it doesn't have to be recursive, but usually when you code divide and conquer recursively, it's simpler to code. But you can still do it, as you see, iteratively. Okay? The second thing is, when you look at this piece of code, it's not easy to conclude that you're using divide and conquer unless you actually trace it. Okay? So this is one observation about divide and conquer. Not all pieces of code that looks like they're not divide and conquer, that are not recursive basically, are not using divide and conquer. This is using divide and conquer for sure. Okay? So divide and conquer could be coded iteratively, and the solution will look like a variation usually of binary search in many cases, and then you can start concluding, okay, this is actually divide and conquering. Okay. There's also something here. I spent some time in the previous lecture talking about the leftmost one, but this doesn't appear here, but it is in the logic. It is in the logic of behind this code, but it doesn't explicitly appear. Okay. So this is something you have to learn, that in many cases the observations that you come up with when developing or before developing a divide and conquer approach might not manifest themselves directly in the code, but they will be there embedded between the lines. Like, this is really taking care of having the leftmost one being our target and not anyone. Okay? Now, it doesn't show up again here, but it is there. You will just have to visualize the code, even trace it, to convince yourself that it is actually there, that we will get the leftmost one and not anyone. Okay? Now, I've actually amended those lecture slides by adding another kind of related example under the same number, which is the same problem we looked at, but for an unsorted array. Okay? So, you have the ones and zeros intermingled together. And the question becomes, can you come up with a divide and conquer approach that finds the first one? Okay? Now, before you jump into designing a divide and conquer algorithm, try to build some observations. And if you look at the examples I've cited here, your first observation should be the one could be anywhere. Your second observation is that because the zeros and ones are intermingled together, I cannot ignore a half like I did before and work with the second half. It does not make sense because the one could be anywhere. Okay? So let me read the observations again. The first one could be anywhere, so ignoring a subarray after dividing into two subarrays does not help. I mean by that, the notion of saving computational time by ignoring a subarray because the answer will never be there is not going to hold here. So what this should invite you to think is this better actually than brute force? And the answer obviously is no. You can come up for sure with a divide and conquer approach. It's going to be, logically like a divide and conquer approach, or it is actually a divide and conquer approach, but the performance is going to be the same as brute force. Okay, and to perform it just as brute force. The code is just going to be slightly different. And instead of writing a for loop that goes from the beginning to the end, looking for the first one, you're going to be doing some index manipulation with low and high like we've seen before, and you keep going back and forth in the two subarrays to find the first one. So in the worst case, both of them will traverse the whole array from the beginning to the end, which is the case if the first one is towards the end of the array. Okay? Now, another observation here is that the left subarray is always more interesting than the right subarray. Okay? Yeah, the ones and zeros are intermingled together, they're mixed, they could be anywhere, but I'm interested in the first one from the left. So the left is always more interesting than the right. So when I'm actually checking, I should always start by checking the left subarray and then the right subarray. Okay? Even though it might appear as the last bit to the right in the left subarray, that still means that the left subarray is more interesting than the right subarray. Okay? So in terms of ordering the processing of the subarrays, I would go left subarray then right subarray, left subarray then right subarray. Okay? So, hopefully that was a nice exercise for you to think about divide and conquer. Let's move on to something a little bit more twisted, I would say. So in this example, what we're interested in is to find how many times we have done rotations through an array. So what is a rotation of an array? Suppose you have a sorted set of numbers from 1 to 10. A rotation here means I will take a number from the end, which is 10, and rotate it and put it at the front. So instead of the numbers being 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, if I do one rotation, it's going to be, I will take 10 and put it at the front, so it's going to be 10, 1, 2, 3, 4, 5, 6, 7, 8, 9. Now, this problem is asking for the following. It's going to give you an array, you're given an array, and you're asked how many times we've done rotations. So if you look at the array that says 15, 18, 2, 3, 6, 12, the initial array was, as it's written down there, 2, 3, 6, 12, 15, 18. If I do one rotation, I take the 18 and put it at the front. So the array becomes 18, 2, 3, 6, 12, 15. If I do a second rotation, it's going to be the 15 and put it at the front of the 18, so it's going to be the one we're looking at here in the big font. Is going to be 15, 18, 2, 3, 6, 12. So the number of rotations here, or the k, is 2. So the question is, design a divide and conquer algorithm that calculates the k, that finds the k. If you look at the example down below, it says 7, 9, 11, 12, 5. The initial input was 5, 7, 9, 11, 12. That's the number sorted. Now, to get this array we're looking at, 7, 9, 11, 12, 5, we must have made 4 rotations. We got the 12 first, and then followed by the 11, followed by the 9, followed by the 7. So the answer here, the k, is equal to 4. If you look at the example way at the bottom, 7, 9, 11, 12, 15, the number of rotations obviously is 0 because the values is sorted. So I'm always started with a sorted array, and the rotations changes how the array is organized. So this is a little bit more subtle than what you would think of at the beginning. Let's try to look at these examples and come up with observations that will help us later to design the divide and conquer algorithm. So if you look at 15, 18, 2, 3, 6, 12, we said the rotations is 2. And if you look at 7, 9, 11, 12, and 5, the rotations is 4. And if you look at 7, 9, 11, 12, 15, the rotations is 0. So when I design a divide and conquer algorithm, I will be dividing this array, okay? Because this is divide and conquer. But when I'm dividing, I don't know what to look for. So my observations has to be related to that. What to look for, okay? Now, I don't want you, when you're designing or thinking of divide and conquer, to fall back or regress to brute force. This is very common when students see this for the first time. So you will start telling me, you will know that you're regressing or falling back to brute force if you start thinking like this. First of all, if you start thinking of for loops. You look at this and say, okay, if I write a for loop that tries to compare. Once you say this, I say, okay, you're not doing divide and conquer. What you need to do with divide and conquer is divide. So you're going to get this array and you're going to divide it. So the question is, after you divide, what are you supposed to do? And this goes back to the issue of observations. You have to generate here some really clever observations. Okay? Now I will tell you one and then we will read it again in the next slide. The index of the smallest value is k, is the number of rotations. If you look at 2, the index of 2 is 2, 0, 1, 2. 15 is in location 0 in the array, 18 is in location 1 in the array, 2 is in location 2. The index of 5 at the second example is 4, 0, 1, 2, 3, 4. 0 has 7, 1 has 9, and so on. So it's 0, 1, 2, 3, 4. So the index of the smallest number is the number of rotations. And the same thing for the last example. The 7 is in location 0, and it's the smallest number. So this is one observation that is required here. Okay? Now, what's another observation? If you keep looking at these values, you will notice that you will find the smallest number if the number previous to it is greater than it. And if you look at 2, before it is 18. Okay? If you look at 18, before it is 15, it's less than it. If you look at 3, before it is 2, it's less than it. If you look at 6, before it is 3, it's less than it. If you look at 12, before it is 6, it's less than it. But only 2, what's before it, is greater than it. Okay? Same thing for the second example, 5. The number before it is 12. And it's the only case where the number before it is bigger. Because if you look at 12, the number before it is 11, it's smaller. If you look at 11, the number before it is 9, smaller. Look at 9, the number before it is 7, smaller. Okay? So these are two important observations, because when you divide, you have to look for something that will help you to find the k. And what you will look for is the smallest value, actually. So instead of actually trying to figure out by brute force how many times we did rotations, what the divide and conquer solution here will be doing is we will split the array, and then what we're doing is we're looking at the number in the middle to see if the number before it is greater than it. And if the number before it is greater than it, then this must be the smallest number. And if this is the smallest number, its index is going to be k. So here's the observations again I was just describing to you. The index of the smallest element is the number of rotations. The smallest element is the only element whose previous is greater than it. Okay? The third one, when splitting, and if mid is not equal to minimum, then can we ignore one of the two sub-arrays coming from the division? Let's think about that. I'm going to leave it for you to think about it. Okay? Try to decide. Now, to answer the last question, let's simulate all rotations on a small array. Okay? So, what you see here in the first line, 1, 2, 3, 4, 5, 6, 7, 8, 9. The next line, I've rotated the 9. So it becomes 9 all the way, and then 1 to 8. And then I rotate the 8, so it goes after the 9. And I rotate the 7, I rotate the 5, the 6, the 5, the 4, the 3, the 2, the 1. Okay? So this is how it looks now. The last line stays 2, 3, 4, 5, 6, 7, 8, 9, 1. Okay? Now, what we're trying to answer here is, can we turn this to like binary search, where we ignore half and work with another half? Can we do that? Don't jump to the conclusion that you can always do this just because you are picking a number in the middle. That would be really an unwise decision. I want you to slow down when you're designing an algorithm and make sure that the decisions you're actually making in the design are sound. So to actually answer the question, can I ignore half and work with the other half or not, that needs some investigation. Okay? Now, let me read the point at the bottom. It says, you should notice that regardless of the current mid chosen, only one subarray will have the minimum with the pattern largest is immediately beside smallest. Okay? Except for the case with zero rotations. So let's do this exercise. Pick any one of the lines above and do a search for the minimum. And ignore one of the two subarrays. Okay? So, let me pick the line that it says, I'm actually count you the line 1, 2, 3, 4, 5. I will pick the fourth line from the top. So it says 7, 8, 9, 1, 2, 3, 4, 5, 6. Now, I will pick a number in the middle. That's how a binary search approach will do. Low plus high, or 0 plus n minus 1 divided by 2 integer division. So I'm going to get, whether I get 2 or 3 doesn't really matter here. Let's say I get 2. Okay? Now, so I got, if 2 is in the middle, so I got the left subarray having 7, 8, 9, 1. And I get the right subarray having 3, 4, 5, 6. So can I ignore one of them and work with the other or not? Well, my minimum is actually is in the left, which is 7, 8, 9, 1. It's the 1. Now, can I really ignore the right? Can I really ignore the right? That's the question. Can I ignore 3, 4, 5, 6 and just work with 7, 8, 9, 1? Well, if I ignore 3, 4, 5, 6, that means since the pattern is increasing, it will never decrease. Because if it decreases, I can get the minimum. But if it continuously increases, then ignoring it is okay, because the minimum is not going to be there. Now, this is a bit subtle, right? So you need to really think slowly here and understand what's going on. Okay? Now, I need to figure out if it's continuously increasing or not. Can I do that? Yeah, sure. I will pick the first, in the right subarray, which is 3, 4, 5, 6. I will pick the first number and the last number, 3 and 6. Okay? Now, 3 is less than 6. So between them, there got to be increasing numbers. It's got to be 4, it's got to be 5, and then got to be 6. Okay? I can't have 3, 4, 3, 2, 1, 5, 6. It's impossible because of the way rotations are doing. So if I check the first number and the last number, and I can see that actually the last number is bigger than the first number in the right subarray, then for sure I can ignore it, and I'm very happy. I know that I'm not actually missing my minimum. It will never be there. Okay? Now, this only can be done if the numbers are continuously increasing. Now, if you look at the left side of 2, where I have 7, 8, 9, 1, the numbers are increasing and then decreasing. So the first one is big, which is 7, much bigger than the 1. So I don't know. I cannot ignore that. But if the 3, 4, 5, 6 was the 3, 4, 5, 6, yes, I can ignore it. Okay? Let's pick the last, the third line from the bottom. It says 4, 5, 6, 7. Again, just to stress the point. 4, 5, 6, 7. And then 8, 9, 1, 2, 3. So, if I pick 8 as the midpoint, and then I check the two subarrays, the left is saying 4, 5, 6, 7. So if I check 4 and 5 and 7, well, okay, it looks like it's increasing from 4 to 7. So the minimum cannot be there. and since the minimum cannot be there, the minimum is going to be to the right. So it's enough for me to figure out which one of them has an increasing sequence of numbers, and then that is enough to actually conclude that I can ignore it and work with the other half, because the minimum is going to be there. I hope that's clear. So, again, here is the summary of our algorithm. The divide step, I will divide the array to two parts using the midpoint, just like in binary search. The conquer, I will compare mid minus 1, mid and mid plus 1 to determine if minimum is mid or mid plus 1. If minimum is not found, then ignore the subarray with increasing sequence and divide the other one. Okay? So I hope this is clear by now, because we just went into discussion about all of this. And then finally I will return the index of the minimum. And here's the code. Again, I got this from Geeks for Geeks. So it will look very much like binary search, unsurprisingly, because it uses the same approach with a twist. So again, what's passed here is an array, the low and the high. If the high is less than the low, then they have crossed, I will return 0. Okay? And this actually means that the array is not rotated at all. You should actually be able to trace this and convince yourself that this is my base case to handle the case where the array is not rotated at all. Okay? It's a sorted set of numbers. Now, if high is equal to low, I will return low. There's only one element left. Else, I'll calculate the mid. Okay, I'm calculating the mid here in the correct way. If you remember from CS3 days, this is the right way to actually find the midpoint. And then I check the following. I say if mid is less than high, an array of mid plus 1 is less than array of mid, then return mid plus 1. Okay? Are you following? I don't think so, right? Let's look at this case. 3, 4, 5, 1, 2. The mid is going to be pointing to 5. Okay? Because it's going to be integer division, so 5 is going to be my mid. So if I say if mid is less than high, okay, let's say high is going to be pointing to 2, the last element. An array of mid plus 1, which is going to be 1, the smallest value in the array, is less than array of mid, which means 1 is less than 5. It is the case. Okay? Then I will return mid plus 1. I will return the minimum, which is mid plus 1, or basically the index of the minimum, which is mid plus 1. Okay? Now, what's the second if statement then? That says check if mid itself is a minimum element. Well, if mid is greater than low, just as a sanity check, an array of mid is less than array of mid minus 1. Okay? Yeah. Let's imagine that we in the array above we switched the values. It's 3, 4, 1, 1.5, and 2. Okay? So 3, 4, 1, 1.5, and 2. And when you pick the mid, now it's 1. So I want to check if this mid is actually less than the number after it. Sorry, before it. That's array of mid minus 1. That's, it's 3, 4, 1, 1.5, and 2. So I want to check that 1 is less than 4. And if it's the case, then I will return mid, because this will be the minimum. Because as we said, the minimum is the only number when we do rotations, but the number before it is greater than it. So this is going to be 3, 4, 1, 1.5, and 2, and 1 will be the mid. So 4 is before it, and this is the check I'm doing here. Okay? Now, otherwise, I will have to check for the condition I was just describing. If array of high is greater than array of mid, okay, then I have an increasing sequence of numbers, and I will work with the left half, because as you see, the statement after that is return count rotations array low mid minus 1, which means it's the left half. Else I will work with the right half, which is similar logic to binary search, if you remember. The next problem we're going to look at is the maximum segment sum, which is a little bit more complex than what we have seen before. The requirement here is to find an adjacent or contiguous set of numbers whose sum is the largest for the whole array of unsorted numbers with negative and positive values. So you're going to get an array that looks like this, 2 minus 5, 8 minus 6, 10, and minus 2. There are positive numbers, there are negative numbers, and they're not sorted. What we want to do is we want to find the set of adjacent numbers whose sum is largest in this array. So obviously a brute force approach here will be ridiculous. You will sum all adjacent pairs. So you go 2 minus 5, you will sum that, and then you will sum 2 minus 5 and 8, and then you will sum 2 minus 5 and 8 and minus 6, and then you will sum 2 minus 5, 8, minus 6 and 10, and then you will sum 2 minus 5, 8, minus 6, 10, and minus 2. And then you try minus 5 and 8, minus 5, 8, and minus 6, minus 5, 8, minus 6, 10. And it goes like this for all adjacent numbers. So it's going to be really expensive to actually do it brute force. What we need to do is to come up with a divide and conquer approach that help us to find the largest sum. In many ways, this is kind of the complement of the shortest distance between 2 points on a graph that we have discussed before. Okay, there are a lot of similarities between both of them. So for this specific array, the largest actually sequence is going to be 8 minus 6 and 10, which will give you 12. But the question is, how can we actually come up with a divide and conquer algorithm that solve this problem? Now again, divide and conquer means you're going to divide the data. So obviously, I'm going to pick a midpoint in this array. I'm going to split this array into 2 halves, and I will recursively or continuously keep doing that until actually I don't need to do any further splits because I'm working with a trivial size array. Let's just think of this slowly. Okay, if I do the split, let's say if you look at this array, I split it the minus 6. So I will have 2 minus 5, 8 in one subarray, and minus 6, 10, and minus 2 in another subarray. What am I supposed to do then? I'm supposed to keep splitting, and then ultimately my conquering will be doing the addition. I have to do the addition. I have to figure out what is the sum of every adjacent pair or every adjacent set of numbers. And then I will come out from the recursion or from the conquering step with these values that represent the largest sum in every side. Okay, so I will look at 2 minus 5 and 8 as if this is only the array I have, and I'll figure out what's the largest sum I can bring up or I can generate here. So 2 and minus 5, that's a minus 3. Minus 5 and 8, that's a 3. So it's minus 5 and 8 because the result is 3. Okay, while 2 and minus 5 is going to give me minus 3. And by the way, it has to be contiguous, so I cannot jump numbers. I cannot say 2 and 8. I cannot try that. It has to be, they have to be adjacent. So I will try, if I look at the subarray of 2 minus 5 and 8, I will try 2 minus 5, and I will try minus 5 and 8. So then my answer is going to be, okay, the largest sum is 3 because it's the minus 5 and 8. Now I'll do the same thing on the other side. I will do, okay, minus 6 and 10, that'll be a 4. And then 10 and minus 2, that'll be an 8. So it's an 8. So in the right array, I'm going to get an 8. With the right subarray, I'm going to get an 8 as the largest sum. And on the left subarray, I'm going to get 3. So the largest sum is like, okay, 8. But then we run into the same issue with this. We've seen with the closest pair problem. What if there are pairs that start in one subarray, or what are the sequences, sorry, what are the sequences that starts in one subarray and continue on to the next subarray, okay, to the adjacent subarray, and it starts in the left subarray and continue on to the right subarray, and their sum is actually bigger than anything else we have seen. Okay, so Again, that's why, there is some similarity between this and the closest pair graph problem, and I think I'm giving you enough insights. Okay, so let's move on and see how we're gonna approach it. So this is to stress the point. Okay, we're going to divide. Divide and conquer means you're going to divide the data. Okay, so I'm going to divide the problem into 2 or more instances. Again, here is an example. 2 minus 5 and 8, one we were looking at, and minus 6, 10, and minus 2. Okay, the division is easy here. I have to do the division because I will save computations this way, because I will calculate what you could think of as local maximum in each one of those subarrays. So what about the conquering step? Now, in the conquering step, what we want to do is we want to keep reducing the problem into smaller subproblems until we conquer it easily. What's the easiest thing you can do here? The easiest thing is to find the sum of a segment that consists of a single element, because that will be the value of the element itself. And that's what we're going to do. We're going to stop at the level of an array that has one value, and the sum of that segment is going to be that value. Okay? So the base case is going to be, if I'm looking at one element, is going to be return that element. Okay? And if you'd like to extend this, if I'm looking at an array that has no elements, then its sum is 0. I cannot return a negative number because a negative number will change my weights or my calculations. But it's 0 when added up to my summation is not going to change the summation. So you can actually stop here in one of 2 ways. Either you stop at an array that has one element and your result is going to be returning the sum of that element, which is the element itself, or you could stop at an array that has 0 elements, at an empty array, and then you return 0, so you don't affect your computations. Okay? So somewhat similar to what we have done before, I will calculate with the closest pair, I will calculate the max segment sum in array A from low to mid, and also I will calculate max segment sum, I'm referring to the 2 lines at the bottom here, for array A starting from mid plus 1 all the way till the end. So if I have an array of 100 values, 100 numbers, I will call this function with the left half from 0, say, to 49, and I will call this same function again max segment, max seg sum for the same array from location 50 to location 99. What about in the combine? Now, max seg sum will find to me the largest sum of a segment, a contiguous set of values. So I will calculate that for the left subarray, I will calculate that for the right subarray, assuming mid is in the middle. And should I just pick the largest of the 2? We said no, because we have a problem with crossing values that cross from one subarray to the adjacent subarray. Okay, and so what we're going to do in the combine, we are going to actually do 3 calculations. We are going to calculate or grab the maximum sum from the left subarray and grab the maximum sum from the right subarray, and also calculate what's called the max crossing or the crossing max, which is the maximum sum we can obtain from the segment that exists in these 2 subarrays. What that means, we will have to start from the middle and keep adding one element from this side and one element from the other side, one element from the right, one element from the left, and keep computing the maximum. until we hit a value that is smaller than the maximum, so we stop. This is the rationale behind it. And then now we have three maximums: left max, right max, and crossing max. We pick the maximum of the three. Now the implementation on Geeks for Geeks, if you actually look up this online, the first hit that always appears is Geeks for Geeks implementation. It's a little bit trickier than what you would expect. What I had just described could be coded just as what I have described. But what actually they are doing here is a little bit more subtle. It's a little bit more optimized for sure than what I'm describing. So let's look at it, but I'm not going to spend lots of time on it because you could code the implementation, I believe, of what I just described, and you don't have to do it this way. This is a little bit more harder to understand, I would say. But even and it's the reason why it's coded like that, because it's more efficient. Okay, so let's look at the code bit by bit. So we have this method called max sub array sum. It takes the array, it takes a low and a high. It's going to be 0 and n-1 when we start. And in the base case, if the low is equal to the high, I will just return, the array itself, the array element I'm looking at, and this is basically saying the maximum sum of an array that has one element is that element itself. Now, if low is not equal to high, then low is somewhere different index. I will do low plus high divided by 2 to get the midpoint. And then I will calculate the three maximum we just discussed. Maximum in the left subarray, which goes max subarray sum array LM, so left to mid, and maximum subarray sum array mid plus 1 to h, to high, and then maximum crossing sum array low, mid, and high. Each one of those functions will return to me a maximum. The first one is to me the maximum in the left half, second one the maximum in the right half, third one the crossing maximum, which is involving elements that exist in the middle, in the left and right subarray. I pick the maximum of the three and I'm done. Okay, so this is what we have been describing. Now, let me tell you about the implementation I'm going to show you, which I got from Geeks for Geeks, and it's very popular for this problem because it's more efficient in terms of coding than what I have been describing as the logic. The logic is sound, what I just described. You could code the logic I'm just describing. So you write three, or basically two functions, one to calculate the maximum in a subarray, and you either pass it the left or the right, and one to calculate the crossing maximum. But there is another way to do it, and this is really the part that kind of annoys some students. When you're actually calculating the crossing maximum, let's read what I wrote here. It says you start from the mid, extend the segment all the way to the left, and get the maximum segment sum for the left side. Plus, start from the mid, extend the segment all the way to the right, get the maximum segment sum for the right side. So basically, I know where is the mid. When I'm calculating the max crossing, I know where is the mid. I will go from the mid towards the left, all the way to the beginning of the array, and I will go from the mid to the right, all the way till the end of the array, to get the crossing maximum. But when I'm doing actually that, am I not also calculating the maximum in the left subarray? Am I not also calculating the maximum in the right subarray? And the answer is yes, because I will start from the mid and go to the left, and when I'm done, I will start from the mid and go to the right. So I'm basically extending to the left and to the right, and I can keep extending all the way till the end of till both ends. On the right, far right, I reach the -2, and far left, I reach the 2. Okay. So the actual implementation that exists on Geeks for Geeks, what it's doing is it's doing all the logic in crossing, max crossing. Okay, it's doing it to calculate the maximum of the left subarray, the maximum of the right subarray, and the crossing maximum. Okay, and this is why students, whenever they look at this piece of code, they find it confusing, because it's not just calculating the max crossing; it's doing all the work actually. Okay, there's nothing else left after this guy is done. Okay? Now, let's go back to the code. The code we've seen before is on the left here. Going back to the statement at the bottom of the gray area, it says return max subarray sum. Where is this call in? It's in a method called max subarray sum. So max subarray sum is not actually doing anything. As if you look back, up, I'm just passing it different indices, low and high. Otherwise, it's not doing anything useful. Okay? It's not really looking for anything. It's not computing any maximum. Who's doing all the work? It's max crossing sum. Now, max crossing sum is on the right, and if you look at the different pieces in the code, it says the first block, it says include elements on the left of the mid, and then the next block, it says include elements on right of the mid. Okay. Now, I will leave this code for you to trace because I don't want to spend lots of time on working out the details of the for loop. But what I'm going to give you as a summary is that when it says include elements on left of the mid, this for loop that appears in the fourth line that says for int I am I greater than or equal to 1, I minus minus, I start from the midpoint and I go all the way till I equal to 1. So I'm moving towards the left. And as you see here, I'm accumulating the values of the array in the sum local variable. Okay? I will leave this if statement for you to understand. Why am I saying if sum greater than left sum, then left sum is equal to sum? And then the same logic is repeated but for the right side. And then finally, I return left sum plus right sum. So I'm just, giving to you as a exercise. This is really not about the logic of divide and conquer. We understand the logic, except here the implementation is different from what I described. It's doing everything in one place, which is a maximum crossing sum. So this is doing the maximum of the left subarray, which is in the first for loop, the right subarray, the next for loop, and somehow this is merged at the last statement. Okay, so I will leave this as an exercise for you to figure it out. Okay, it's actually straightforward. You just have to trace it to get the idea of why it's done like this. And this is done just again for efficiency reasons. We could have changed the code so that I write a real method that says it calculates maximum subarray sum. Okay, so I could call this method, for example, max sig, the one at the left. So that has the documentation. Return sum of maximum sum array subarray in AA1 L to L dot H. Okay, I could have called this max sig, and then written a method called max subarray sum, and call it twice for left and right, and call another one max crossing sum that only does the crossing. Okay. But again, this implementation is more efficient. That's why it's more commonly used. So let's summarize. Divide and conquer. What's the advantages? Well, the big advantage of divide and conquer is that if you're faced with a problem that's too difficult to come up with a solution for it, then applying divide and conquer helps you a lot. Okay? We've seen this over and over in many of the problems, and I'm not really talking here about when I say it's difficult to come up with a solution for that you cannot write a brute force solution. I'm saying that the brute force solution is going to be really expensive, and consequently you are trying to avoid that expensive cost. Okay? Breaking the problem into parts just helps you a lot with performance. Now, there is something also you need to be aware of. Why divide and conquer is actually a very interesting design strategy. There are many very, very difficult problems in computer science that could be difficult in terms of how slow we can solve them. That we have solutions for them, but the solutions are really slow because they're like n to the 7 or n to the 8. One way of actually speeding up the execution of slow algorithms is to use parallelism. Now, parallelism as a topic is not anymore that exciting and hot research area as it used to be. When I was in my undergrad studies, I studied a language called concurrent C, which is a C version of C language that runs on multiple processors at the same time, and there's a special compiler for it and so on. Now, the thing is, there is another way you can go about solving very complex problems. If you can come up with a divide and conquer solution for a very complex problem, most likely your divide and conquer solution is going to be also expensive. So there are certain problems in graph algorithms, for example, where brute force solutions would be, say, n to the 8. And when you come up with a divide and conquer approach, it's going to be n to the 4, which is good. It's good, actually, okay? It's still like horrible in terms of you'd like it to get it like in log n or O of 1, but n to the 4 is much better than n to the 8. But still it is going to be slow. So the thing is, with divide and conquer, because of the way we think when we design a divide and conquer solution, by dividing the problem into smaller problems, what we could do is, we could, after dividing the problem into smaller problems, send each one of those subproblems to be solved separately or conquered separately on a different processors. And this has become, again, a hot idea with the introduction of multi-core processors. Like nowadays, you have quad cores, you have processors that have 4 and 8 cores in the same package. What this means, you could run a program, if it's done properly, or an algorithm, if it's done properly, on 4 processors at the same time. And so you can speed it up. So even though your divide and conquer is still not that, star in terms of performance, with multiple processors nowadays, just the notion of dividing the problem to smaller problems helps you a lot. Okay, so there is a revived interest in parallelism in a divide and conquer context because of that. Okay. By this we finish divide and conquer. You will see many problems in the practice assignment. Okay, and you will be given also additional problems to work on your own, just to get you thinking using divide and conquer. What we're going to look at next is another design strategy, okay, that is much simpler as an idea than divide and conquer. Divide and conquer is a little bit complex in the sense that you have to understand how to divide, you have to understand how to conquer. The division is usually straightforward. The conquering and combination is related to the quality of your observations given a specific problem. Now with greedy, the whole thing becomes a little bit more naive, I would say. So if you ask me, what's the merit or essence of the greedy design method? And my answer is going to be as simple as, be greedy in the choices in front of you. Don't think ahead. Don't think strategically. Don't try to be smarter than an average person developing a greedy algorithm. As naive as it sounds, sometimes this works and enables you to come up with algorithms that solve complex problems. And sometimes it doesn't work, as we will see. So the essence of being greedy is that you don't look ahead. If you think, for example, of nutrition styles, someone who likes to eat lots of carbs, kunafa, basbousa, ais saraya, and so on, and they don't follow a healthy diet, is trying to achieve what's called instant gratification. When you get the sugar into the blood, you get immediately excited. But you don't think strategically. For someone who's doing that, he's not thinking strategically. If you eat lots of carbs, you might end up developing diabetes or having heart problems in the future. They just think about the options immediately in front of them, which is to eat carbs or not to eat carbs. And since the mental and physiological reward of eating lots of carbs is very strong, they decide to eat lots of carbs. Okay. Now, talking about it more formally and leaving a healthy diet aside or unhealthy diet aside, here is a more formal approach to the greedy method. In the greedy method, we talk about configurations and some objective function. Configurations refer to the choices, the data, the collections of data items, the collection of items, if you like, the collection of inputs that is available to you to choose from at any specific instance. The objective function is what you use to make a pick of a specific item from the choices or data items in front of you. So if you go back to healthy eating or unhealthy eating, the objective function is the amount of reward you feel when you eat lots of carbs. So since the more carbs you eat, the more you feel the adrenaline rush into your blood, that would be your objective function. You could think of any type of data, and when you're asked to make a choice, to make a pick, as long as you have some objective function that you can apply, or in other words, you pass the data to, and the objective function will tell you which data item is best to pick now. And as long as you can pass the data to the objective function, so you have these configurations. If you have these two components, configurations and objective function, then you can come up with a greedy algorithm for your problem. Now, you could formulate a greedy strategy for almost anything, but the question is it an optimal solution or not? And is it efficient or not? Even if it's not optimal, but is it efficient or not? So we'll talk more about that. Now I'm trying here in this slide to illustrate to you the way a greedy algorithm will work. You have inputs or data items that are ready for you to process. You pass them to a specific objective function that you write. Now, the objective function could be as simple as minimum, maximum, or a very complex function that has many variables that maybe you compute from the data. But the objective function tells you which one to select. What that means is one of the data items, after running the inputs or passing the inputs to the objective function, one of the data items, the inputs, will disappear because it has been selected by the objective function. What that means is you will keep selecting one at a time in a greedy way from your available inputs until ultimately there is no more inputs. Now, the idea is simple, as you see, but the formulation here is actually what requires some imagination from your part when you are developing or defining the configuration and developing the objective function. Now, as I mentioned, objective functions could either be quite simple or could be complex, like multivariate, using multivariate calculus to decide on which data item to pick. Okay? Now, an underlying assumption here is that the data items are pickable in the sense that you can pick one and ignore the rest. Okay? Now, according to the classical way of thinking about greedy algorithms, there are no mention or restrictions set on how you formulate the configurations, or in other words, how much effort you do in formulating the configurations. But since we're mentioning this, it does not make sense to do a massive computational effort to be able to run an efficient greedy algorithm. Because in order to do the efficient, to run or to execute the efficient greedy algorithm, you'll have to pay a price, which is the massive computational effort upfront to prepare the objective functions. What this means is that you apply greedy when the configurations are readily available. It's in the problem statement basically. Okay. So I will come to this point shortly again, but what I want you to remember is objective functions are a mathematical function that you pass it the data items and it picks one of them and says, okay, I'm going to choose this now. And we say this is a greedy approach because all our decisions or any specific decision we make is based on what we currently have and what the objective function is telling us. there is no look into the future or trying to attempt to go back in one of our decisions. When we make a decision to pick an item, we don't go back, even though if we discover actually that pick was not good down the road. We can't undo. Okay? That's why it's greedy. You make a choice based on what you know now, and if it turns out to be a bad choice later on, well, you're unlucky. You'll have to pay a price for that. So again, configurations, the most important thing to remember is that if you decide to pick a greedy algorithm design for a specific problem, you have to be very conscious and vigilant, I would say, about the readiness of the data to be turned to a configuration. Okay? The best thing is actually the data itself is the configuration. You don't do any pre-processing or preparation of the data. Okay? If you think this is a little bit theoretical, just wait until we start seeing the examples. So, before we start seeing the examples, let's go over the steps. I've tried here to formulate it in terms of steps. So whenever you think you get a question like design a greedy algorithm to so and so, and you should be able to do that in a systematic way. Step number 1, state your input configuration. Okay, what is your input? Step number 2, state your goal. What are you trying to achieve? Okay, based on your goal, you will develop an objective function. Okay, and then step number 4 and 5 are trivial. You apply your objective function on the available input on configuration, and step number 5, you keep doing step number 4 until you're done. Okay, now again, as a word of caution, if you cannot formulate it this way, you're not doing greedy. Okay, you're not doing greedy. So you have to have configurations, you have to have a goal, you have to have an objective function based on the goal or trying to achieve the goal. And when you apply an objective function, your data size should reduce. Okay, it should reduce by 1 or n or whatever, but it should reduce. Okay, so if you're not doing it as I'm describing, let's say for example in step number 4 or 5, when you apply the objective function, the data is not reduced, but at the end, ultimately, when you reach to some state, you say you're done, but you haven't reduced the input space, then you're not really doing greedy. Okay, this is the merit of greedy is that you have to be reducing the input space as you keep running the objective function or passing the data to the objective function so that it picks one of them. So we will look at several examples. Again, just to make you think of how you apply this algorithm, and they vary a lot in terms of the nature of the problem. So let's start. The first one we're going to look at is called the counting money problem. Very simple problem, and very complex actually to get right. Now, the idea is like this. In any country, you have monetary units. Okay, you have values attached to the different currency units they are using. So, for example, if you look at U.S. dollars, or the U.S. system, there's 1 cent, 10 cents, 25 cents, $1, $5, $10, $20, $50, and $100. Okay, so that's your input. Your input configuration. You have an unlimited supply of currency from some monetary system. Okay, like for example the U.S. Monetary system. Now, notice here I'm saying unlimited supply, and this might be a little bit surprising or alerting to some, because usually we don't have unlimited supply of data, but because this is a simple problem, so we'll just leave it at that. We're not going to really discuss it from a mathematical point of view. Now, what is our goal here? You must have a clear goal. Our goal is quite simple. In fact, you could have played this game when you're a young child, which is to make a specific value using the fewest possible bills and coins. Okay? So, for example, if I tell you make $100 US, the fewest possible bills and coins is one paper of worth $100. $100. Okay? You could make it out of 250s or 520s or 1010s, but then I want the fewest possible bills and coins. So 100 will be just one piece of paper and written on it the value 100. Now, my objective function is I will select the largest possible bill or coin as long as it does not overshoot. Okay, so my objective function, I will pass it the monetary values, and I will pass it what I'm trying to make as a sum, and it will pick from the past values the largest value that exists in the input, as long as the total sum up till now did not exceed my target. Okay, so let's look at a run of this objective function on our monetary system. So let's say for the same US monetary system, we would like to make $6.39. So the objective function will sort the dollars from largest to smallest. 100 will not work, 50 will not work, 20 will not work, 10 will not work, 5 will work, so it picks a 5. Okay? Because again, the objective function is picking the largest value that is less than the sum. The sum is currently 0 and my target is 6.39. So I will pick a 5. And then I will try to pick another 5, but the sum will exceed, it will be 10, so it will not pick another 5, it will pick the next best candidate, which is 1. It will add it, the total will be 6. And then it will try to add another 1, but then the total will be exceeded, it will be 7, so, or the target will be exceeded, it will be 7, so it will pick 25. And then it tries to add another 25, it does not work, it's going to be 6.5, so it skips the 25 and it adds a 10. And then it will add a 1, it becomes 636, and then another one, 637, 638, 639, and then we've reached our target. You see, it has to be done, and you have to be thinking of the algorithm the same way I'm describing it. Okay, you have to follow the objective function very, very closely. Okay, if you say select the largest possible bill or coin, and that means if you're past a set of bills and coins, you don't be smart about it. You just apply the objective function. It says pick the largest. So you pick 100 and try. You pick 50 and try. You pick 20 and try. You pick 10 and try, and it goes like this. Okay. Now, so for the US system, and it's not surprising that we will make 639 with the smallest possible set of units or currencies or values. Okay. So, are there other ways we can make? Yes, of course. We can make 639 with 639 1 cents. Okay? Or we could make it with 60 tens. Okay? Actually, a little bit more than that. Or we could make it with 24 or 25 25s. Actually, 4, yeah, 4. Yeah, okay, so 4 by 6 is 24, so you can make it with 25 25s. Okay? Now, or you could make it with six $1. Okay? But the smallest possible set of coins and bills could be produced for this specific configuration using this specific objective function. Okay? But this will not always work, as the last point says. Okay? So, in another, say, fictional monetary system where I only have 1 kron, 7 kron, and 10 kron coins, and I would like to make 15. So according to our objective function, we're going to pick a 10. And then we try to add the 7, so we're going to get 17. So we skip the 7, and then we try the 1. So we go from 10 to 11, 12, 13, 14, 15. So it's basically 1 10 and 5 1s. Now, obviously, if you look carefully at the monetary system we're looking at here, how many coins did we use? It's going to be 1 10 and 5 5. So that's 6 of them, 6 coins. But actually, you can do it in, obviously, 3. You can use 2 7s and 1 kron and 1 1. So that would be 3 coins. Okay? Now, according to our objective function, the result is going to be 1 10 and 5 crons. And this result we say is not optimal, obviously, because there is a better solution, as I mentioned. And this is the thing about greedy algorithms. Greedy algorithms are not, it's not a guarantee that you will get an optimal solution from greedy algorithms. Okay? Why? Because you're being greedy. You're just picking what's in front of you, and you're always being greedy. Okay? So being greedy means picking the largest, okay, or picking the path that you think if you go through, it's going to be better for you. Maybe because the scenery is more beautiful, okay? But you will arrive late. So again, you pick a criteria and you follow it blindly. You don't go back. So after picking the 110, when we look at the next option and we see the 7, we should deduce, I mean, intelligently, or even you could think of it like as an algorithm. Oh, why don't I just deduce? Oh, when I see the 7, let's drop the 10 and try the 7. And then try 1 7 and then a second 7 and then we get the 1. But we can't do that with greedy, because greedy says largest, biggest, okay, strongest, tallest, and so on, heaviest. So we always work with the thing that we think that is going to be best in terms of the immediate reward. So when we see a 10, because it's less than 15, we immediately pick it and we say, okay, now we have 110 and this is part of our solution. We don't go back when we see the 7 again. Okay? So generally, many greedy algorithms will give you the solution. Okay? But the question is it giving you an optimal solution? And this is not an easy question, actually. Sometimes it's very difficult to answer. Okay? Let's look at another problem, a little bit trickier. This is called the scheduling problem. So, in the scheduling problem, what you have is a number of jobs. Each one has a specific running time, and the running times are different from each other. For example, for 9 jobs, these are the running times. This is a very classical problem in the operating system world, in the shipping and containers world, in the scheduling of tasks in an assembly line in a factory, and so on. Okay? Anywhere where you have jobs and they take different amounts of time. Now, in this specific incarnation of the problem, we're thinking of it as an operating system problem. So let's say I have 9 processes, and this is the time it's going to take to run each one of them. And I have 3 processors, okay, that I could use to execute those processes or jobs. Now, my goal is to schedule them in a way so that all the jobs finished in the shortest possible time, which kind of makes sense. You know, if you have lots of tasks and you'd like to finish as fast as possible, every task is taking a different amount of time, and you have 3 processors or 3 machines that you could use. The question is, which order of admission should I allow for these different jobs so that I can finish as fast as possible? So my objective is going to be, again, greedy is not complex. Greedy is quite simple. It's always being greedy means picking longest, largest, tallest, heaviest, most enjoyable, and so on. Okay? So I'm going to pick the longest running job first. Okay? The rationale here is that when I finish the long one first, the shorter ones are going to take less time. So I could be quickly, or first I will be going slowly running the longest jobs. Slowly here means slow as is throughput, how many actually I can do per second. So at the beginning my rate is going to be slow. Okay? The definition of throughput you should have seen in the operating system course. It's basically how many jobs can you finish per second. So when you run a long job, your throughput is going to be slow because you didn't finish in the first minute or the second minute or the third minute or the fourth minute and so on. So if I actually pick the longest running jobs first, my throughput is going to be slow at the beginning, and then as I finish the longest ones and I start picking the shorter ones, my throughput will quickly, jump up, and I will be able to finish fast. That's the rationale behind this. It might not be exactly the correct rationale, but this is the greedy way of thinking again. Okay? So let's actually do that. Let's try to run it and see. Notice here that this is a problem that, regardless of it creates an optimal solution or not, the problem yields itself to a greedy algorithm, because the configurations are jobs I'm going to pick from them using the objective function, and ultimately my jobs will finish. And this is again what I want to see in a configuration, that the data at the end is gone. There is no more to process in terms of data items. Okay, so picking the longest means I will pick the 21st. So here are my three processors. I will put in the first processor P1, I will put the job that takes 20 minutes, and in the second processor I will put the job that takes 18 minutes, and in the third I will put the job that takes 15 minutes. And then obviously the first one that's going to finish is the shorter of the three, so the 15 minutes will finish first, and immediately I put the 14 minutes after it. Okay, and then the 18 finishes, so I put the 11 minutes after it, and then the 10 is put after the 20. And of the three currently running, say 11 will finish first, so I put the 6, and then the 14, so I put the 5, and then the 3, I put it after the 10. Okay, so again here, there is not lots of intelligence involved. I'm basically applying the objective function. Okay, now, so the total time to completion is going to be, the time of the longest one, which is 18 plus 11 plus 6, which is 35 minutes. Okay, it's not a bad strategy, but the question is it optimal or not? And I will tell you it is not. Okay, we actually can do better, and let me show you. Here is another variation before I show you the better approach. Let's reverse the objective function. Okay, now the rationale here is going to be, if you'd like to apply it this way, is that if I put the shortest ones first, what I'm going to do is I will finish as many of them as I can possibly early on finish. Okay, so if I put the shortest one first, I could say that I've just finished in the first maybe minute half of them. Okay, so that's another way of thinking about it. Okay, now so again, here are my results. I will put the shorter ones first, followed by the longer ones. And here, actually, this is not performing as good as the previous solution. This is actually will finish in 40 minutes. Okay, which is the time that will be taken by P3, because it's the longest of the three. Now, can we do better? Obviously, yes. If you're already into algorithm design, you know that we could use something called dynamic programming. We'll talk about it later on. And in dynamic programming, we will try different combinations to get the optimal solution, and the optimal solution is going to be 34 minutes instead of 35 minutes. Okay? So we'll see that later on. Now, this is an example of a greedy algorithm that people use. Okay, so this is actually used in certain operating systems. At least the early versions of Linux, the operating system, used to use a greedy approach that allocates longer processes first compared to shorter processes. Now here is obviously the assumption is that you know how much time a process will take, and that is typical in certain kinds of jobs that are called batch jobs or offline jobs. But obviously if this is an interactive job, then you can't run any of this. Okay, so it's used in certain job types inside the operating system. Okay, so we have to have upfront knowledge about how much time it's going to take. Let's see another example applying the greedy approach. But before we do that, I would like to quickly just refresh you with some graph terminology. Okay? Now, first of all, let me tell you this. You should never forget your graphs or your graph information. It's a very popular interview question, and it's a very important data structure because it is the most generic data structure compared to all other data structures that you have learned. In fact, we could specialize a graph to create any data structure, okay, including linked lists and trees, binary search trees, and so on. Okay. Now, this is a huge area, by the way. Okay. In fact, it's the most important area in computer science theory, graph theory. They have their own journals, and they're quite interesting kind of people you would see doing or solving problems in the graph theory world. Okay, mostly mathematicians and some computer scientists as well. Okay. Anyway, let me refresh your memory with graphs. Why are we again interested in graphs? They have tons of applications. In fact, throughout this course, we will see a number of algorithms that are used all over the places, from routers. If you have a router at home, like from TE Data or from Vodafone or from Etisalat or whatever, it has a graph algorithm. Okay, most likely one of the ones we're going to talk about here in the course. Okay, but it doesn't just apply to routers. In civil engineering, there's a whole area called transportation engineering that people who study transportation engineering are responsible for the planning of the traffic and the construction of bridges and tunnels and subways in a city is all under the the supervision of transportation engineers. Okay, and they all model a city as a graph, and the cars moving as objects that move on the edges of the graph. It's very popular actually as an area. Same thing for electronics and so on. In fact, even when you access your Facebook, it's a graph. So friends of friends of friends, they're basically edges or arcs in a graph. So let's do some formal definitions quickly. If you're bored, just hold on with me. If you know this stuff, just hold on with me for just a few slides, and then we'll start the real stuff. So formally, a graph is a pair of vertices and edges. Okay, vertices are the ovals that you see there, and the edges are the arcs that connect these ovals. Okay, now what else can we say? We have two types of edges. We have directed edges and undirected edges. Now, in a directed edge, you go from one vertex to another, but you cannot go back. Like, for example, here you have a flight from ORD going to PVD, but not the other way around. Okay? Now, if the edge does not have an arrowhead, then you can go in either direction. You can go from ORD to PVD or PVD to ORD. Okay? And that would be called an undirected edge. Now, based on the type of the edge, you either have a directed graph or an undirected graph, and you cannot mix them. Either you have directed or you have undirected in terms of graphs and edges. Okay? Now, why do we differentiate between them, by the way? Because the algorithm that works on directed graphs will not work on undirected graphs usually, okay, and the reverse as well. Okay? So it's important to know up front what kind of graph you're working with. Now, we have several labels related to edges and vertices. So when we talk about end vertices of an edge, I mean the two vertices that reside on both sides of an edge. So U and V are the end vertices of A, for example. Okay? And when we talk about edges incident on a vertex, like for example A, D, and B over here are all incident on V, while E and F are incident on W, and so on. We talk about adjacent vertices, meaning that two vertices are connected by an edge, like for example X and Z. Okay? We talk about the degree of a vertex, which is how many edges are going to a specific or the specific vertex we are referring to. Like for example here, Y degree is 2 because it has G and F connected to it. Okay? We'll also talk about parallel edges, where you have two edges that will take you back and forth between two vertices like H and I. Okay? And we also have loops as well, as you see with J. Now, let's go to the important stuff. A path in a graph is a sequence of vertices and edges. And they have to be alternating because you jump from one vertex to another using an edge. Okay? So we talk about it as U, A, V, B, X, H, Z, for example. Okay? Always begins with a vertex and always ends with a vertex. Okay? Now, let's talk about passes. So a simple pass is a pass such that all its vertices and edges are distinct. So for example, U, C, W, F, Y is a simple pass. Okay? Or the other one I have put down here in red, VB. So if you trace this, VB, X, H, Z is a pass. It's a simple pass. Okay? Now, the one that is highlighted in green is not a simple pass because I pass by W twice. I go UCW, EX, G, Y, F, W again, and then DV. Okay, so this is not a simple pass. Now, another type of pass where we have a cycle. We start at some vertex, and we keep going inside the graph, and then finally we find ourselves again standing at the same vertex. Okay? Now, we have variations of cycles actually, and the one we're interested in is what's called a simple cycle, where all the vertices and edges are distinct, which means we start from one and we end up on that same one, that same vertex, but along the way we don't have loops. Okay? So for example, the one highlighted in red here, it's a simple cycle because I start with V and I end up back in V. Okay? But along the way I did not visit a vertex or a node more than once. Now, while W is not a simple cycle, because I keep going back and forth on W, the one in green. Now, subgraphs are a subset of a graph, okay, where all the vertices in the subgraph exist in the original graph. A special type of a subgraph is what's called a spanning subgraph. So a spanning subgraph spans all the graph, which means you have all the vertices, but not all the edges. Okay? So a subgraph could be spanning, or it could be non-spanning. If it's non-spanning, that means you got this maybe 50 vertices connected together, and then you pick a number of them, let's say 20 of them, and you create a subgraph from that. But if you create a subgraph where you have all the nodes but not all the edges, then we call that a spanning subgraph, because this means you have access to all the vertices in the graph. Okay? And what that means is that the edges that you've included in the subgraph, in the spanning subgraph, must be taking you to all these vertices. And the ones that you omitted must be not that useful to you, that's why you've omitted. But you can still go to all the vertices. Now, we'll also define the notion of a connected graph. So a graph is connected if there is a path between every pair of vertices. Again, a graph is connected if there is a path between every pair of vertices. That means you can go everywhere. Now, a disconnected graph, a non-connected graph, is one where you have components that resides in a subgraph, more than one subgraph, but they are not necessarily all connected to each other, like the one you see at the bottom right here. Okay? Now, why am I going into this lengthy introduction to graphs? Well, I like to do that for two reasons. First of all, I'm going to show you a number of algorithms along the way in this course that works on graphs, so I need to make sure that you understand the different terminology. And number two, this is an excellent, actually, opportunity to introduce graphs. It's a very huge area, and they have tons of algorithms. Okay, you can check the graphs algorithms page on Wikipedia. You will be surprised. They have like lots and lots of algorithms. They're very complex, but they're very popular. And nowadays, with the rise of social networks and mobile applications and so on, it becomes extremely important that you get exposed to this. Okay, so, and you will find the algorithms are classified by what they work on. So they will tell you this works on a graph that has simple cycles but not non-simple cycles, or they will tell you this works on a connected graph, or this works on a non-connected graph, and so on. Now you know what's a forest and what's a tree. Let's look at a special kind of a tree, which is called the spanning tree. So this is a tree according to our definition in the previous slide, but it has this nice property that it includes all the vertices in a graph, but not necessarily all the edges. The idea here is that we want a mechanism to traverse all the nodes or vertices in a graph. In a typical graph application, if you say, for example, if you're modeling the traffic in a city, or you're modeling friends and friends of friends on Facebook using a graph, you could have hundreds of thousands or even millions of vertices. And you could have millions or tens of millions of edges in a single graph. If you're trying to visit all the nodes or all the vertices to do anything, like for example, print the name of the person stored inside a vertex, or collect some property or some characteristic of each customer, where this is a graph of customers. So there is always a need to actually visit all the vertices in a graph. So you need to be able to do that in an efficient way. And what you could do actually, given a huge graph, is to run an algorithm that generates a spanning tree from the graph, and then you traverse the spanning tree, and instead of traversing the original graph or the input graph. So while the original graph might have, say, 1 million vertices and 5 million edges, the spanning tree will still have the 1 million vertices, but perhaps 1.2 million or 1.5 million edges. This notion that we can disregard many edges is quite powerful, because I just need enough edges to visit all the vertices. I don't have to have all the edges. In fact, by generating a spanning tree, we get rid of a very nasty problem in the graph world, which is the existence of cycles, because we said a tree has no cycles. And this is very important, because when you actually try to traverse a graph that has cycles, you might end up going back to a node or a vertex that you've seen before. But if you are actually visiting the spanning tree generated from a graph, since there are no cycles in a tree, you will never go into an infinite loop going back and forth between the same set of vertices. And when you're actually traversing this tree, ultimately you will visit all the vertices, which would be your initial goal. Okay, so there is a need for spanning trees in the graph world, and there has been many algorithms that tries to generate spanning trees and do generate spanning trees from graphs. Okay, this is basically the classical way of traversing a graph, which is, given a huge graph, run an algorithm that generates a spanning tree, and then traverse the spanning tree instead of traversing the original graph. Okay. Now, what we're going to look next, I'm giving you all this lengthy introduction to graphs because I would like to show you an algorithm that uses the greedy approach to generate spanning trees. It actually generates a very special type of spanning trees called minimum spanning trees. Now, so let's again model the algorithm the same way we have described before, working with a greedy or working through a greedy design process. Step number 1, what's your input? The input here is a forest consisting of multiple graphs. Okay, so this algorithm will work nicely not just on a tree, it works on a forest of trees. Now, for this algorithm to work, each edge must be assigned some cost or weight. The edge cost or weight could be the distance between two vertices if your graph is representing a map. So you would have a vertex for Cairo and a vertex for Alexandria, and the edge will be labeled, say, 220 kilometers or 220 basically for the distance between Cairo and Alexandria. Now, the second step in our greedy design process, we said we would like to clearly spell out the goal that we're trying to achieve. So Kruskal is an algorithm that generates minimum spanning trees. Minimum spanning trees means the total sum of the values or weights of the edges will be as least as possible. Okay? If you have read before about graphs, you should get a sense that, okay, this goes like, it's an interesting approach, because if I have this huge graph, I could traverse all the vertices with the least cost. Okay, this kind of connects you with the traveling salesman problem if you have seen it before. If not, don't worry about it. The next step, we have to understand Kruskal objective function. This is how the thinking goes. We would like to build a minimum spanning tree, or often it's abbreviated as MST. Minimum means the cost on the edges is as small as possible. The total cost on the edges is as small as possible. So, given a graph on the left, which is basically a forest, what Kruskal will produce are the set of red edges shown on the right side drawing. Notice that it's actually a tree. So if you look closely at the right side, you have a forest of two graphs. The first one, you have A, B, C, E, D vertices, and Kruskal decided to include or build this tree with the 1 edge, the 5 edge, the 8 edge, and the 3 edge. And for the second subgraph, which includes the G, F, and H vertices, Kruskal produced or selected 2 and 4 to be the edges in this tree. So what Kruskal gives you as an output is not just a spanning tree. As you see here, we can reach to all vertices, so this is a spanning tree, but it's giving you a minimum spanning tree where the total sum of the values on the edges is as low as possible. Okay, it's the minimum. And you can check that right away by looking at the right side subgraph for the G, F, and H. Notice that it picked 4 and 2. Had it picked 2 and 6, the total would have been 8, which is more than 4 and 2. Had it picked 4 and 6, the total would have been 10. So 2 and 6, it would have been 8. 4 and 6, it would have been 10. So it picked 2 and 4 to be able to reach to all the vertices, but with the lowest cost possible on the edges. So it is time now to actually understand what is Kruskal objective function. This is how it works. Remember, this is greedy. We have to have a greedy merit here. What we are trying to do is build a tree that is spanning all the subgraph that we're working with, or the graph that we're working with, sorry. Now, so what Kruskal does, the objective function, is as follows. It will imagine that we have taken out all the edges with their values or with their cost from the given input graph. So you look at the graph at the left side, we are seeing two subgraphs. One of them actually has a cycle, and the other one also has a cycle, and there are many edges. You got, from A to B, you got an edge labeled 1, and then from B to C you got an edge labeled 5, and from A to C you got an edge labeled 7, and so on. So we will, the algorithm works like this. We will imagine that we have removed all the edges and we're just keeping the vertices. Removed means here we took them aside, we put them somewhere, and then we sort them from smallest to largest. So if we get all of these guys and we sort them, we're going to get the values 1, then 2, then 3, then 4, then 5, then 6, then 7, then 8, then 9, then 10, then 11. Now, so the objective function says that let's scan through the sorted list of edges, pick the smallest one first. This is the greedy part. Pick the smallest one first and add it back to the graph and check if there is a cycle. If there is no cycle, keep it. So what this means, we're going to see, or the objective function will pick 1 first. 1 is connecting A to B. So it will add it to the graph. And then it will pick 2 next, because 2 comes after 1, and then it will add it to the graph. That will go between H and F. And then it will pick 3, and then add it to the graph. After adding every edge to a graph or a subgraph, it will check for cycles. Now, if you're already into graphs, you know that sounds like a bit scary, because checking for cycles is not trivial in the graph world. Yes, it's not trivial, but this is how this algorithm works. You add an edge, and then you check if there is a cycle. Why are we checking if there is a cycle? Because remember, a minimum spanning tree is a tree, and a tree has no cycles. So we pick 3 and we add it to the graph and check if there is no cycles. We pick 4, we add it to the graph and check if there is no cycle, we're going to keep it. The merit here is that the following: we are trying to generate a spanning tree that has the minimum cost. So let's pick and work with the edges, and let's accept the edges that have the smallest cost possible. And we can do that by sorting the edges and pick the smallest one first. Okay? Now, it will, after adding the 4 between G and F, is going to find the 5. It's going to pick the 5 because it's immediately after the 4. Okay? Now, so it adds it to B and C and check if there is a cycle. There is no cycle. And then again, it will pick the next one, which is going to be a 6. So it adds it to the, the subgraph to the right between G and H, and then check if there is a cycle, and it discovers there is a cycle. So it removes the 6 away and throw it away. Okay? And then it gets the 7. It will add it as an edge between A and C and check for a cycle, and it immediately recognizes, oh, there is a cycle, because we can go A, B, C, A, B, C, A, B, C, there is a cycle, so it will just remove 7 away and not add it to its minimum spanning tree output. And then it will add the 8 and check if there's a cycle. There's no cycle, so it will keep the 8 between B and E. And then it gets the 9, it adds it between C and E, and again, there is a cycle. The cycle goes BCE, 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 and so on. So it's going to remove the 9 as if it doesn't exist. And then it adds the 10 and checks. And obviously there will be a cycle, because you could go A, B, E, D, A, B, E, D, and so on. So it will remove away the 10. And then it adds the 11. And again, it will find that there is a cycle, because you can go B, C, D, E, and then again B, C, D, E. So that's again a cycle, so it removes away the 11. And finally, you're done, because there's no more edges to consider. Now, what you end up with as output is a minimum spanning tree. If you add up the values in the left subgraph, which is 1 and 5 is 6 and 8 is 14 and 3 is 17, there is no better or smaller value minimum spanning tree than that. If you add the 1 on the right, we already worked that out. 2 and 4 is 6. The other alternatives would have been 8, which is 2 and 6, and 10, which is 6 and 4. So 2 and 4 is actually the correct choice in terms of being the minimum. Now here is again a visualization of what I have been describing. We start from the graph at the top left. We add the edge and check for cycles. As you see, the edges are being added in order of smallest to largest in terms of edge value or edge cost or edge weight until we are done. So we'll add the 1, we'll add the 2, we'll add the 3. After every addition, the algorithm goes and checks for a cycle. This is a continuation of what I was just describing. We add the 4, next we add the 5, next we add the 6, no, the 7, no, the 8 is added, and then we are done. Here are the references for today's lecture. I am, as you see, including the specific pages that you need to read if you have missed any of the details in today's lecture. And you can download the text from the link given. And if you get too excited about graph algorithms, I've included a link for you that is optional. You should see it to figure out how big is the graph theory area. They have like lots and lots of very useful algorithms. And if you actually work in any company that is classified as a social networks company, like for example Google with its different applications, or Facebook or Twitter or Quora, then you will be again seeing many other graph algorithms in your career. Thank you.